All right, ladies and gentlemen, so we are going to start with an intro to waves. On this slide, you have vocab words that you are going to need to know, all right? If you're following along, we're on review book pages 82 to 84, okay? All right, so electromagnetic energy, that's going to be the energy that is radiated or released during transverse waves, which is what we are going to be working with mostly, all right? The crest is going to be the highest part, and the trough is going to be the lowest part, okay? Then you have frequency, amplitude, and wavelength. Okay, we're going to go over what each of these means, and I'm going to teach it to you through a video, okay? And then we're going to label a wave together on Notability. So I am actually joining on my iPad as we speak. Okay, so I will be in the background. Okay, so let's watch the video, and we'll be pausing it as time goes on.
Waves. One of the first things we need to know about waves is there are two different types of wave. One, shown here, by waves in the sea. The other one, shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves.
All right, we're taking notes. Right, so transverse waves, they are waves that run perpendicular to the direction of travel. And the direction of travel is basically your x-axis, is the best way to think of it as.
Examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky. This time, the direction of vibration is parallel.
Okay, so in this case, okay, the waves are parallel to the direction of travel. They don't go up and then down. They actually will go on the direction of travel. This is also, with sound waves specifically, this is where you get the fact that as it moves towards you, it gets louder, and then once it passes you, it gets lower. When, like, if you're standing on the side of the street, like on 188th, and an ambulance drives by or a fire truck drives by, as it's getting closer to you, right, this would be how you hear it once the sound is very close to you, and then it disappears.
To the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy.
Oh, that's really important. That's that energy that we were just talking about, that electromagnetic energy, right, are going to be transferred or through waves.
From place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. Wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off,
First thing you're going to want to do, guys, is draw this in your notes. Exactly how you see it. Okay, because he's going to label it, and it's probably easier if you label it with him, and I'm going to stop like I've been doing. But if you have this in your notes, it makes life a lot easier. You guys ready?
Almost.
Okay.
Okay.
Wavelength. The wavelength is the length of a full cycle of a wave.
All right. So wavelength is going to be the length of a full cycle of the wave. So it's represented by this Greek lowercase letter of lambda. Okay. The way that you are going to figure it out, it's basically one full cycle. So if I wanted to look at the wavelength, I could say it starts here. This is all the same wave. This is all the same wave. Nothing has repeated yet. Nothing has repeated yet. And then starting the next wave. So this whole thing here would be one full wavelength. So what he's going to tell you, and I'm going to tell you, the easiest way to do this is by measuring it from the top of one wave to the top of the next wave, or the bottom of one wave or the bottom of the next wave. Okay? The top parts are known as the crest, and that bottom point is known as the trough.
Cycle of a wave. From one point to the next.
Okay? So the easiest way to do it, like I said, is from crest to crest or trough to trough. But in this example here, you can pick any random spot on a wavelength as long as you hit that same random spot on the second wave. Then that'll be your wavelength as well.
Same point. It's easiest to think of as the distance from crest to crest or from trough to trough.
Okay, so like I said, the highest point is going to be the crest, the lowest point is going to be the trough. Series at a timer for 110.
Wait, what was the lowest again?
It says it right here, the trough.
Oh, okay, thank you.
No problem.
We measure it in meters. It's given the symbol lambda. Nice Greeks. The amplitude is like the size of a wave, but we need to remember that it's measured from the equilibrium position, the central line, to the crest, not from the crest to the trough.
Okay, so the amplitude is basically going to be the height. All right, so you can measure it from this x-axis looking thing, or he calls it the equilibrium line. Okay, it's measured from there to the highest point, or from there to the crest, or from there to the trough. Either way, that's going to be your amplitude.
Finally, frequency, which is the number of complete waves.
Okay, so I'm going to let you guys copy that down. So frequency is the number of complete waves per second. All right, so it's how many waves that you have completed in 1 second. All right, by looking at this, all right, if you have a very large wavelength or a very large distance between two waves, what do you think the frequency is going to be? Is it going to be high or is it going to be low?
Low.
Why? Come on, you got to back up your answer.
Is it because it's cyclic?
It's not because it's cyclic. The waves are cyclic. But if you have a wavelength that's very large, it means that your wave is going to go do, 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 do. It's going to be a very large wave, or a very large distance between one wave and the other. So its frequency is going to be low because there's not a lot of waves that are happening. But if your wave is going do, 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 really quickly or really close together, that means you have a smaller wavelength, but you've included a larger number of waves, and therefore your frequency is higher. So what kind of a relationship is there between frequency and wavelength? right? If the wavelength is high and the frequency is low, what kind of a relationship is that?
Would it be kind of like indirect?
Indirect, exactly. That's exactly what it is. It's an indirect relationship. All right, so let's look at this.
Pass a point every second. It's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave. Using the equation, speed equals frequency times wavelength. Or, to give it in symbol form, V equals F lambda. So there's a lot to learn here. Once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
Okay, so I want to go back a little bit so that you can see this, right? So where did he go? Where did he go? Where did he go? Here. Okay. So he's saying that you've completed 10 waves in 2 seconds, right? So the frequency is going to be very high, right? How do I know? Because it's how many cycles you've passed or how many waves you've gone through in how many seconds. So it's 10 divided by 2, which is 5, right? Notice that the wavelength, or the distance between one wave and the next wave, is much smaller than you would expect because you're increasing the amount of waves that are happening, right? And having it be an indirect relationship makes it that way. All right, so why do people see colors differently, right? Well, it's because colors are getting reflected and absorbed. Like we said yesterday with Uranus and Neptune, right? We see it as blue planets because the blue wavelength is being reflected. All the other colors are being absorbed, right? So my white shirt, the reason why we see this as a white shirt is because all of the colors are being reflected. Okay, if you have a black shirt, it means that all colors are going to be absorbed. Okay, we've talked about infrared radiation and ultraviolet radiation, how from the sun the UV rays come in and it gets absorbed into the ground and then gets distributed back out as IR radiation, okay? Now, or infrared radiation. Now, when I was talking about the greenhouse effect, I said that UV comes in, but it will not allow all of the infrared radiation to leave. The reason is because of their wavelengths, all right? Ultraviolet rays are short waves, so it's easier for them to come through. Infrared radiation are long waves, so it's harder for them to go through the greenhouse, or in the case of Venus, the cloud cover, and it ends up heating up inside of Venus or inside of that greenhouse, because you're literally trapping the waves inside of it, which then in turn reheats it, and so on and so forth. Okay? Now, if you were looking at your reference table, page 14, you have this. Okay, the only thing that you do not have is the actual wavelength sizes. I still don't understand why they took that out, but they did. Okay, so let's look at the reference table. Okay. Right, so page 14, you guys are all looking at page 14, right? Here we are. Here's the electromagnetic spectrum. That's the light that gets basically shot out, all right? So we have things like radio waves, microwaves, infrared, and ultraviolet. Notice how they're very close together. So there's not much of a difference between the two, but there is still some, right? The X-rays and the gamma rays, all right? On here, notice that frequency is not listed, but you are to know that it is an indirect relationship. So if I decrease the wavelength, which means there's less of a distance between each of the waves, it means that there's going to be a lot of waves happening. If I increase the distance between each of the waves, it means that it's not going to be a lot of waves in a short period of time. Okay? Gamma rays over here are basically can go through everything but 6 inches of concrete. Do not try to hang out with gamma rays thinking you are going to become the Hulk, because you're not. Okay? Gamma rays are very harmful to the body. All right? The Hulk is a story. Okay, so we don't want to do anything silly. That's why if you look, all of the bomb shelters, or it'll say on some of the older buildings, if you're going through, if you're walking by a building, down by the basement door, there's usually a black sign with a little radiation symbol in yellow on it. It's a fallout shelter. The reason why they have those is it depends on when the building was built, but between World War II and the Cold War, they were always afraid that people were going to bomb us, so they created basically areas in buildings that would keep out gamma rays, okay, because it is such a large and harmful thing. All right, so let's talk about stars. All right, so we know that stars, there's a lot of information that I'm about to give you, but stars in general, all right, stars are born, they live, and they die. Just like a human, there's a life cycle of a star, okay? They come in all sizes, right? There's smalls, there's medium smalls, there's mediums, there's medium larges, there's larges, there's extra larges, okay? So they all come in different sizes. And if you remember back to the video I showed you of the sizes of the planets, and then all of a sudden I was like, here's our sun. Then it was like, here's Betelgeuse, and it was way bigger, right? Because our sun is a medium-sized, middle-aged star, okay? Down here, you see 3 different versions of what's known as a galaxy. A galaxy is basically a grouping of stars and solar systems together. We're assuming that since we have a solar system, that there's probably multiple of them around. This one down here on the left is a version of the Milky Way galaxy, okay? The Milky Way galaxy, which is where we are, right, is a spiral galaxy, and we are not at the center of it. I told you this when we did another video. We're somewhere on the arm of the galaxy, okay? So, stars are just like, it's not like the sun is by itself. Stars are, the rest of the stars are just like it. They're made up of burning hot balls of gas, okay? Which means that the process of fusion is happening over and over and over and over again, where you're taking those hydrogen atoms and you are forcing them together to overcome that nuclear repulsion, and you're creating a helium atom, okay? That energy that is being released is going to be that electromagnetic energy that we were talking about. Now remember, radiated and released are basically the same thing. Okay, so if ever you see the word radiated, I want you to write the word released. Okay, so because of this nuclear fusion that's coming out, you're radiating electromagnetic energy, which ends up being in that colored spectrum that you saw on Earth Science Reference Table, page 14. Your version of it is in black and white. The one that I showed you on the PowerPoint was actually in color. And so if you don't know what your color spectrum is or what the colors are, don't you worry, as I have a little video for you to look at. You know, there's going to be a commercial first, because that's just what they do now.
We just had the most amazing family vacation.
Get out of your head, and you will never forget the colors of the spectrum. Okay? So now you know what they are, in order, so on and so forth. Okay? All right, so let's talk about these characteristics of stars. Like I said before, even though they're going to be larger than our star, right? They're going to vary in size. They're not all one size fits all, which means that they're going to have a different mass. They're going to have a different density. They're going to have a different temperature, which tells me that they're going to be a different color, because the color variation is dependent on temperature. Okay? Talking about that color change, right? It's also going to be luminosity, or it's going to be different brightness of the star. Okay? This will depend upon the star's size and temperature. Okay? So all of this, you're never going to have to memorize. You're going to have to know what luminosity means. But we do have an Earth Science reference table for that. And if you look at page 15, where our nice chart is, there's a characteristics of stars chart on top of it. Okay, that's also known as a Hertzsprung-Russell diagram, which we will get into a little bit later, not by much. Okay, so luminosity is how bright that star is. And it's always going to be in comparison to our sun, because you're going to compare it to things you know. If a star is brighter than our sun, then it's going to be more luminous, okay? And if it's going to be duller than our sun, then it is going to be less luminous. You guys okay with that?
Yes.
Okay. So, let's talk about the composition. Now, the composition of stars will vary, but it might not vary as much as you think, because they're primarily all started with hydrogen and it formed helium. Now, it will continue to glow until all of the hydrogen is used up, but the hydrogens aren't the only things that are moving, right? The helium molecules are also moving as well. So as they're moving, eventually they're going to fuse together, right, and become bigger elements, right? But it's taking longer than they expected for that. So there are other elements there, but they're in very small amounts compared to hydrogen and helium, which you would expect. Okay? Now, there's this stuff called spectral analysis, and this is when I wish we were in school, because it's so cool to actually see through spectroscopes, but unfortunately I do not have those here. I will, however, show you on the internet, and you can Google it yourself. There's a couple of different things there that you can look at. All right, so wavelengths, right? We said that everything has a different wavelength, okay? Hydrogen specifically is going to have a different bright line spectra, which is basically the final thing of when you're doing spectral analysis. Spectral analysis is when you take something and you break it down into its elemental form. What is it going to look like? Okay, so each element and each compound are going to have a different spectrum. Okay, I call it the fingerprint of elements and compounds. So if you looked at hydrogen's spectral analysis versus helium spectral analysis versus water spectral analysis, which is H2O, they're all going to be different. That's why I call them the fingerprint, right? Because your fingerprint is different than anybody else's out there. Don't get involved with twins, because most of the time twins do have different fingerprints. There are times when they have very, 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 very similar ones, but there is something that's different of them. Okay? All right, so like I was saying, spectral analysis, it's the study of electromagnetic spectrum, or that emission, or that radiated energy, okay, specifically by a star during the process of fusion using a spectroscope. Okay, spectroscope is just the instrument. And the ones that we have at school are little pieces of plastic. Okay? All right? Like I was saying, each element has its own set of wavelengths. And if I were you, I would 110% put in there like a fingerprint. Let me see if I can find it real quick. While you guys are copying that down. The heck? All right, so this goes back to what we were just saying on page 14. Right, so we're going to be dealing with the visible light spectrum. All right, so let me see if it'll let me do this really quick. I like this one better. All right, let's join the meet. Join the meet. Join. Trying to join and it's not letting me. Okay, so what you see here, it gets there, all right, is actually the fingerprint of each of these elements, okay? Notice how they're all different, all right? There are numbers that go with it, but for our level, we do not need to know the numbers, okay? Right, when you're looking at this, you have hydrogen, which has a bunch of the violet and indigo, and then it has the blue, and then it has a red. But then you look down here at neon, and it's completely different. Some of the lines are thicker, some of the lines are thinner, okay? So they are all going to be completely different when you are looking at this, okay? So let's see if I can find one specifically for a star. Let's go with Betelgeuse. Okay, so the one of Betelgeuse, this one looks good. Okay, you can see that it's not just going to be made up of. You see how it's blurred together like that? But if you look right here, okay, hopefully it'll let me stay there. Okay, you can see little lines that are being, okay, that are in between. The problem with the extra things, the blurred lines like that, is, see, look, here's a bunch of them. Right? So you see how with like the first one, you have a line here of blue and then a line of orange and then a line of red. Okay, and I will post this, guys, for you. These are all just different ones. Now, the fact that it's blurry like that tells me that there's background radiation, okay, that's interfering with it. All right, when it is continuous like that, when it's a continuous spectrum, it means there's other things that are also being picked up. So you're going to want to look for the little tiny lines. And what scientists will do, they will not only run this through the spectroscope and be able to see what's happening, but then also they will compare it to what's known as known elements like hydrogen and helium and carbon and, you know, other things that are known to be in space, okay, and see which ones are in there. So you would compare them to it and see which lines line up. Okay. Let's see if there's a better one. Right, this one kind of looks good. Right, you see all those little lines that are there, right? All the different colors, right? Those lines, they're all different because there are different stars, right? none of these four are going to be the same or exactly the same. Okay, so that's electromagnetic spectrum. All right, it looks like this. Those black lines are, when you actually draw it out, those black lines in the spectrum, or the absorption spectrum, look like underneath it, right? That's going to be the fingerprint. The fact that it has a line of violet, a line of blue, a line of that orangey red color, okay? That will tell me that it is a part of that particular star. Okay? Does anybody have any questions? Okay, well, that's the end of this lesson. So if you guys have any questions, you just let me know.